Welcome to the course on plasma physics and applications. This is the fifth and last module on basic industrial plasmas. In the previous module, we made a qualitative description of plasmas in contact with a wall, and now we will introduce a mathematical description of sheath physics. We will show how to calculate the profiles of potential and density across a sheath. We will find the ion flux across a collisionless sheath. We will calculate the Bohm criterion and also the ion energy across a sheath to a floating wall. This is a revision of the sheath from the previous module. We saw that the plasma potential rises until the fluxes become equal, so we have equal ion and electron flux to the wall. The positive ions are accelerated in the drop of sheath potential from the plasma potential down to the wall potential. This same sheath potential drop has the effect of breaking the electrons to equalize the charged particle fluxes. Now let's introduce some parameters onto our qualitative profile for plasma potential. We say that the potential on the wall is V wall. The potential profile is V of x, where x is the distance from the wall, and V plasma is the potential of the plasma, which is equipotential at a large distance from the wall. We will introduce an arbitrary zero of potential at the edge of the sheath, which will be defined later on, and there is a drop from the plasma potential down to the sheath edge, which we will call delta V pre-sheath. Let's consider the ion velocity in this plasma potential profile. At a far distance from the wall, these cold ions have zero drift velocity in the equipotential profile. As ions approach the sheath edge, they are accelerated across the pre-sheath potential drop, delta V pre-sheath, and they reach a velocity us at the sheath edge. They are further accelerated. Their ion speed increases with a value u of x between the sheath and the wall. Let's consider the conservation of ion energy as they cross the sheath. The energy of the ions as they approach the sheath is a half m(us) squared, and as they cross the sheath, their energy is a half mu squared plus the electric potential as they cross the sheath at this voltage here is in fact negative. If we consider that the sheath is collisionless and therefore there are no collisions, no ionization in the sheath, then conservation of ion flux simply gives that the ion density times the velocity in the sheath is equal to the ion density at the sheath edge times the ion velocity at the sheath edge. Now let's simply eliminate the unknown ion speed in the sheath, u, and we find an expression for the ion density in the sheath. Ion density in the sheath equals the ion density at the sheath edge times this expression. Let's also introduce a profile for the charged particle densities in this situation. In the equipotential plasma, that is, in the bulk plasma, the densities of the electrons equal to the density of ions for a quasi-neutral plasma. N0 equals Ne equals Ni is the density in the plasma. In the pre-sheath, we consider that the plasma is still relatively equipotential, and therefore we have electron density still equal closely to the ion density. At the sheath edge, therefore, the density of electrons and ions are both equal to Ns. This is the quasi-neutral plasma. However, in the sheath, the electron density is strongly reduced, as we saw, due to the sheath potential drop. Therefore, we have the Ne of x electron density profile is lower than the Ni of x, the ion density profile, in the sheath, whose width is S. To summarize, we have the ion density in the sheath from our previous slides, and using the Boltzmann relation, the electron density in the sheath is the electron density at the sheath edge, Ns, times the Boltzmann factor exponential V over electron temperature in the sheath. Now, these two expressions are different because the ion flux is determined by the drift speed of the ions, whereas the electron thermal velocity is much greater than the drift speed and therefore still determined by the Boltzmann relation. Now we introduce Poisson's equation in the sheath, that is, the second differential of voltage with respect to the distance is minus the charge density divided by the vacuum permittivity. The charge density is the ion density minus the electron density multiplied by the magnitude of the electronic charge. We substitute for the charge densities from the previous slide. This is the electron contribution. This is the ion contribution. At the plasma sheath interface, where x is small, we will do a Taylor expansion of these expressions. The exponential appears as 1 plus v over Te, and a binomial expansion introduces this expression here, and we find finally this expression for Poisson's equation. Now, for a physical solution, because we expect the voltage profile to be non-oscillatory with distance, we require the expression in the brackets must be greater than 0. From this inequality, we find an important conclusion, that is that the ion speed entering the sheath, us, has to be bigger than the square root of Ete over m, where Te is the electron temperature in electron volts, therefore Ete is the electron thermal energy in joules, and m is the mass of the ions. Therefore, we see that the ion speed entering the sheath is determined by the ion mass and the electron temperature, not the ion temperature. This inequality, the lower limit, is called the Bohm velocity for ions. This is the Bohm criterion for the ion velocity leaving the plasma and entering the sheath. The Bohm criterion is an important factor in sheath physics. Therefore, we will repeat it here and discuss the conclusions. That is, that the ion velocity depends on the electron temperature. The ions are accelerated to an energy half mUb squared as they enter the sheath. If you work it out, this corresponds to an energy Ete over 2, which the ions gain in crossing the pre-sheath. Now, this corresponds to a pre-sheath potential drop, delta pre-sheath, of Te over 2. Now, this is consistent with Debye screening, which allows potentials of up to Te over 2 to penetrate an equipotential plasma. Now, the plasma density at the sheath edge is Ns times the electron density in the equipotential plasma bulk times the Boltzmann factor crossing the pre-sheath. Electrons are negative. The pre-sheath value is Te over 2 divided by the electron temperature. This gives N0, base of natural logarithms, 1 over the square root. And this works out to be 0.61 N0. That is, that the plasma density at the sheath edge is 61% of the plasma density in the plasma bulk far from the wall. Using this knowledge, we can now go back to our plasma profile and our density profile and start to put some expressions in for the unknown values. The pre-sheath potential drop we found is Te over 2 from the plasma to the sheath edge. The ion velocity approaching the sheath edge is the Bohm criterion velocity. The electron, ion and plasma density approaching the sheath edge is 61% of the charged particle density in the bulk plasma. Now, Debye screening means that the sheath width can only be a few Debye lengths long. Now we have derived Bohm's criterion, we can use it as a tool to calculate other effects in the plasma. For our first example, we will use it to calculate the ion flux, which influences the etch rate in plasma etching. Now first we need to know that Bohm's criterion has some rather general applicability. It seems to apply in many cases, for example radio frequency plasmas, probably because the maximum potential drop which can penetrate a pre-sheath is generally Te/2, and therefore Bohm's criterion tends to have some general validity in many cases. This is part of the great interest in Bohm's criterion. Now the ion flux into a sheath equals the ion flux through the sheath equals the ion flux to the wall because of conservation of ion flux crossing the sheath, that is, no ionization in the sheath. And therefore the ion flux to the wall is the same as the ion flux into the sheath, which is Ns times the Bohm velocity, Ns times the Bohm velocity again. Ns is the plasma density in the bulk divided by the square root of natural logs, which is 61% of the plasma density in the plasma. Now we know that the ion flux to the wall is equal to the electron flux to the wall because the sheath potential appeared in order to guarantee equality of flux. And therefore the electrons and ions, that is the plasma particle loss flux, is given by this expression. In making the statement that the electron flux and ion flux to the wall are both the same, this is the same as stating that there is no current to the wall. We have assumed no current to the wall, that is, we have assumed the wall is electrically floating in this example. Now the ion flux controls the etch rate, as we said at the beginning, and we are now able to calculate also the ion current to a probe of area A. We'll find a current E NSUB times the probe area times this expression. This is a factor very often seen in plasma physics. It's called the ion saturation current to a wall or probe. If the wall is negatively biased, then the Bohm velocity still determines the ion flux into the wall because the ions cannot arrive any faster. In this case, the electron flux is 0. A second consequence of Bohm's criterion is that we can calculate the ion bombardment energy. For equal fluxes to the wall, the ion flux can be equated to the electron flux, and the electron flux is given by the kinetic expression, which is a quarter times the electron density times the electron thermal speed. The electron density is given by Ns times the Boltzmann factor in crossing the sheath, and the electron thermal velocity is 8 ETE over pi ME, where TE is in electron volts. We use the kinetic expression for electrons and not for ions because the thermal velocity of electrons is much, much greater than the drift velocity in these cases. We can now solve this equation for the sheath voltage drop. We find that sheath voltage drop depends on the electron temperature and the natural logarithm of the ratio of ion mass to electron mass with the factor 2 pi. Substituting the values for an argon plasma, we find that this is about 4.7 times the electron temperature. For positive ions with a single charge, we can find the total ion energy which arrives at the wall in joules by adding the ion energy gained across the voltages of the pre-sheath and the sheath. So the total ion energy at the wall is the electric charge times the voltage of the pre-sheath, Te/2, plus the electric charge times the voltage across the sheath. We can factorize this as follows, and we can take the 1 into the natural logs as exponential 1, where e to the power 1 is Euler's number, 2.718. This we can write as ETE/2 natural log ion mass over 2.3 m, And if you put the numbers in for an argon plasma, it's about 5.2 E times TE in electron volts joules. Now this 5.2 EE, ETE, is 4.7 TE plus a half of TE over 2, as you'd expect. Now in books and papers, if you see this expression for the voltage, then this is the voltage across a sheath. If you see this expression for the ion energy, this is the expression for the ion energy across the pre-sheath and the wall. Remember that 5.2 ETE corresponds to an argon plasma. If you have a plasma in different gases, then you have to substitute the relevant mass of the ion, which will change this factor 5.2. To summarize this module, we have calculated the Bohm velocity for ions into a sheath. We've seen that the ion flux to a wall is 61% of the ion density in the plasma times the Bohm velocity. And we have calculated the ion energy of an ion from the plasma to the wall, which is about 5.2 times the electron temperature in volts.